Thank you, Professor Lu. Now, would Professor Jewitt please go on stage to deliver the lecture? Professor Jewitt, please.
So I'll talk about the same basic topic, but in a somewhat different way. So the title of this is What We Know and What We Don't Know about the Kuiper Belt. So I'll talk about both of those things, since they're both interesting. And I'll do it in a style which is accessible as far as that is possible. And I aim to be sweeping and not to be very focused on small details, because I know that for most people the small details are not so interesting in a talk like this. So that's the outline of this talk. I'll give you the summary right at the beginning in case you fall asleep. Then everything will still be okay at the end. So the bottom line is that the solar system is kind of renewed by our work on the Kuiper Belt. Kuiper Belt provides a deep freeze storage location for primordial planetary matter. So the bottom line is it's very, very cold in the Kuiper Belt. Temperatures are like 40 Kelvin, so minus 230 centigrade, something like that, very, very cold. And materials captured in the Kuiper Belt objects in the beginning of solar system time are still there, frozen as solid. So all sorts of materials which are gas and liquid on the Earth, or ice, they're frozen solid in these bodies. Kuiper Belt turns out to provide a source for a whole bunch of other different populations in the solar system that previously were not known to be connected. And so it's allowed us to have this kind of unified view of the solar system with the different populations now clearly related to a single source. So we have a better view of the solar system. And it turns out that different bits of the Kuiper Belt structure tell us different and very interesting things about the origin of the solar system and the evolution of the solar system. And already they tell us far too many things for me to describe them all in this talk. So I've got to be selective, and I'll just talk about a few of the really interesting things that have emerged from the Kuiper Belt. And then lastly, I'll just touch on the point that Kuiper Belt explains to us the solar system in a context provided by other stars. So in fact, we see dusty rings around other stars, and those dusty rings are like a dusty ring in the solar system produced by collisions between Kuiper Belt objects. So I'll go over these things in a little bit of detail, but not too much. Keep in mind there are many, many more things that could be said if we had the time. So I wanted to set this up in the following way by explaining, what, as Jane did a little bit, but in a little bit more detail, what we do and where we do it. And it's pretty clear why we do it. It's because we find out cool things. But here's the way it goes. So we observe from mountaintops to get above the atmosphere and to get above the water vapor in the Earth's atmosphere, principally. And the observatory where most of the work I've done since I went to the US is in Hawaii. It's this shield volcano, 4,000 meters tall, basically centrally located in the Pacific Ocean. And so it's kind of an awesome place to be. You go there, and as Jane said again, you lack oxygen, you feel terrible, you can't breathe properly, you dehydrate. I always point out to people that my wedding ring, which doesn't come off, falls off when I'm on Mauna Kea because of the loss of water. You dehydrate. Over a period of days, your body just, you can see your weight dropping pound by pound. It's because of breathing and transpiration, loss of water. So, and you just feel bad. You have a headache, I have a headache and stomachache, all the rest of it. But it's great to go there, and it's great to go there even though we can now do remote observing through the internet because of the physical experience of suffering in a strange way. It's very impressive. But you also get to see the nature of the mountaintop very clearly. And so the way I like to say that is it gives you the feeling of being a small person on a big planet. Okay, and so it's good to go there just for that reason. And I think people who don't go there, astronomers who like to do it remotely, are really missing out on something that's important. So I wanted to show you the summit a little bit, Those are 3 of the 13 telescopes on the top of Mauna Kea. Again, this is a wintertime picture with snow. In the background, that thing is Maui. It's a nearby volcano. It's a very cool place. When you go to the top, sometimes you encounter wind. In fact, you usually find wind blowing. And the wind itself, even though you can't see it, is staggering. So the wind blows, for example, at 50 miles an hour in your face. So you go up about 5 o'clock in the evening, get ready to observe. The wind is blowing 50 miles an hour in your face. You go out, you can walk around the outside of the dome. You go outside and have a look, see what the sky's like at midnight. The wind is still blowing 50 miles an hour in your face. And then you go out several more times. You go out at sunrise, 6 o'clock in the morning, and the wind is still blowing at 50 miles an hour in your face. It's just completely staggering. And then the next night, you come up again after dinner, about 5 o'clock, 6 o'clock, get ready to set up the telescope, and the wind is still blowing 50 miles an hour in your face from the same direction. And so you just can do the calculation yourself. How far does the wind go at 50 miles an hour in 24 hours? It goes a really long distance. And so it gives you this feeling of being a small person on a big planet, because you can just sense viscerally how big is the Pacific Ocean. And you know the Pacific Ocean is a small thing compared to the size of the Earth, and you know the Earth is small compared to the size of anything else that we're going to talk about today. So that gives you this great feeling of how big things are and how small we are. So here's a movie that shows what you see if you stand outside the telescope and just look, in this case, look east. And so what we have here is the edge of the volcano. This is the edge of the island in black. And we're looking down. I'll start this going. You see that we're looking down on this swirling surface. Here is snow, here is rock, here is cloud. You see things going up. Those are stars rising up above the horizon. It's getting bright here because the sun is about to come up. There's a planet rising. Here comes the sun. Sun is really, really bright. It illuminates the clouds, and you see we're above the clouds, and that's the great thing about this mountain. The clouds are moving because of convection. This is ground heating. And as the sun goes up, ground heating increases, and the clouds boil up. The cloud layer becomes thicker, and you think it's going to come over the top of the mountain, but it doesn't, because the sun goes down through midday, begins to cool, and then the clouds shrink back down. In a moment, here comes the shadow of the mountain on the clouds. Here's the shadow of the Earth on the sky, and then it's nighttime again, and then we see bodies coming up in the sky. And in a moment, the moon rises right here. There comes the moon, and there's the clouds again, and it just goes on and on and on. So that's what it's like to be on Mauna Kea. It's really kind of awesome. There's a public road. You can just drive up there and take a look at this, but it's nice if you have an observatory to hide in, because it's also very, very cold up there. So that's awesome. People who make TV science documentaries know that Mauna Kea is awesome, and they often want to make documentaries of astronomers, and they sometimes call me up and say, hey Dave, we'd really like to come and make a film of you observing on Mauna Kea. And I say, well, yeah, maybe not, because we don't look through the telescope anymore. We use computers to look at the sky. We don't stare through an eyepiece. It's not that interesting. It's just some people typing on a computer, and they say, yeah, but we still want to come out. And so this happened a number of times, and I got tired of it. And so I made the following movie, which shows what it's like to be an astronomer observing. So I could show this movie to the people who want to make TV documentaries, so they can make a more reasonable judgment about whether they want to come out. So this is Astronomy Happening, I call this one. And this is really what you see if you go observing. So here we are, sitting in a control room. This is obviously me. There are computers. This is the Keck Observatory Telescope, the world's biggest telescope. This is Pedro Lacerda, is from Portugal. He's now in Northern Ireland. At this time, he was my postdoc. We're checking things on the computer. We're checking to see whether the telescope is aligned properly. Are we pointed in the right direction? Are the systems doing the right thing? Is the telescope focused? Are we finding our targets or not? Are the mirror segments diverging? Is this thing hanging together because the telescope is this big flexible structure? And it just goes on a lot. We get bored, we go out, we sometimes get a little bit hungry, we come back, okay, come back with the apple, we like to eat, Pedro takes a dive on the floor, we're talking, we're still taking data all the time, it gets cold, we put on a coat, And we keep on going all the way through the night, but basically it's people typing on a computer, talking to the charge-coupled device attached to the telescope far away. So I show this movie to people who want to make TV documentaries, and they still say, yeah, but we want to come out and take our own movie. So it doesn't do any good. But that's what it's like. Okay, so there's your grandmother's solar system. So what we've done basically is take this old picture of the solar system. No offense to grandmothers. Grandmothers are excellent people. But this is the view actually of NASA until really very, very recently. And this view basically shows that the planets are really important. So the artist has drawn the sun and the planets. The planets are proportionally much, much too big. This one is 1/10 of the size of the sun. The Earth is only 1% of the size of the sun. And then you might notice over there's this box, which the artist has called Other. And the artist just threw all this stuff, all those other things which are small, yeah, they're other. Put them in a little box, we don't care about those. And it turns out that everything I'm going to talk about today and everything Jane talked about is in that box. And in fact, the objects in that box, although they're individually small, are extremely scientifically important and valuable and illuminating. They tell us a lot of stuff because the information content of a body is not closely connected to its mass. Just because it's big, it doesn't mean it tells you a lot. In fact, it tells you a lot of different things, but as far as the origin of the solar system is concerned, going into the box called Other has been the big development in the last 20 or 25 years of planetary astronomy, I think. So as a reminder, we know that stars form by collapse of the interstellar medium. And the basic picture is if you get a balloon and squeeze it, make it smaller and let go, the balloon will pop back to its original size. And if you get a bigger balloon and squeeze it and let go, because of the pressure increase inside, it will pop back to its original size. You keep doing that for larger and larger balloons. Eventually, you reach a critical size of balloon, and it's really big. You couldn't put your arms around it. It's way, way bigger than the solar system, in fact. The balloon, when you squeeze it in and let go, doesn't pop back to its original size. It continues to collapse, and it gets smaller and smaller and smaller. And the reason is that the balloon, if it's massive, has its own gravitational field. When you give it the initial compression, make it a little bit denser, if it's at this critical mass, gravity will take over and cause the collapse to continue indefinitely down towards a small central structure. So that was figured out 100 years ago by a person called James Jeans. And now people simulate that in a computer. So here's a cloud of 500 times the mass of the sun. It's made of hydrogen and helium primarily. It starts to collapse, and immediately it densifies. The yellow bits are denser than the red bits. It's moving because the material is falling into the gravitational well defined by all the rest of the material. And so we see these filaments of dense material that appeared. You notice there are little white dots appearing at various places in this movie. It's a simulation by Matthew Bate, by the way, who works in England. And these things are what we call stars. So these are stars formed by the gravitational collapse of gas in the interstellar medium of the galaxy. And then star formation is breaking out here. Now there's a local star formation site. And so what this model tells us is something that we already knew, actually, from observational astronomy. Stars form in groups. You can go out by naked eye with a pair of binoculars and see that young stars sit in clusters, in groups, because they form exactly in this way. Now you can see it's getting very active. There's lots of stuff going on. And then the modeler is zooming out and rotating and doing the fancy stuff that modelers do. But the point is pretty clear. Stars form in groups, and so the idea is that the sun probably formed in a cluster of stars, which is now evaporated. We don't know where our companion stars are. They've drifted off, and they're elsewhere in the galaxy. Now, you can see the skater up there, maybe very small, but the skater starts out spinning with the arms out, and then pulls the arms in, and the spin accelerates because of what's called conservation of angular momentum. Here she goes, going faster and faster and faster. That's the world record skater spin. A spherically collapsing cloud does the same thing. As it collapses, the spin goes up for conservation of angular momentum, and it flattens down and becomes more like a disk. So it immediately explains why the solar system planets orbit in a single plane in the same direction. It's because they formed in this disk. So this movie just flies around a model disk like this. And the essential point is that here's a planet forming in the disk. Here's the sun. This planet has eaten a hole in the disk. There are waves and all sorts of cool things happening. But out here at the edge of this disk, nothing is happening. So in this region, there's basically no planet, no structure. There's not enough time elapsed for anything cool to happen out there. And so that's where we find the Kuiper belt. So the Kuiper belt basically is the place in the solar system where the growth of bodies was so slow that no big bodies could form. Okay, so that's what we discovered. That region of the solar system is shown in this diagram. Here are the orbits of the giant planets. So there's the Sun, there's Jupiter, Saturn, Uranus, and Neptune, and this one again is Pluto. And the diameter of this system is about 100 times the distance between the Earth and the Sun. So that's it. It's our local icebox because the Sun is far away and it's very, very cold there. And then Jane already showed you this image. This is how we find them, simply by comparing images in which all other parts of the universe, these things are galaxies. Every other dot in here is a galaxy. Those things are held fixed. And the Kuiper belt object marches by because it's in orbit around the Sun. And so it's Keplerian motion around the Sun that carries it across our sky. So that's how we found them. Now here's the only technical diagram that I have in this talk. And I'll just go through it. It's not that bad. Here is the distance from the Sun. So this is 20 AUs, and this is 100 AUs from the Sun. Okay, so it's radial distance from the Sun. And then this one is the shape of the orbit, the eccentricity, with 0 being a circular orbit and 0.8 being elliptical like that, kind of extreme egg-shaped at the top. So it's just a convenient way to plot the orbits of the objects that we've discovered in the Kuiper belt. We have 1,500 objects. I didn't plot 1,500 dots because there would be too many. But you can already see a couple of things. First of all, not all regions of this diagram are equally occupied. Okay, so there's certain preferred locations in the semi-major axis eccentricity plane. And so there's a reason for that. The dynamical subtypes of the objects, none of which were predicted, seem to be very clear. But second of all, there are different flavors of Kuiper belt object, and I'll just talk very briefly about some of those different flavors. So the red ones, the first object we discovered was actually one of the red ones. We call them the classical Kuiper belt objects. These bodies have small eccentricities. The eccentricity is 0.1. It means the shape of the orbit is like that. And they're out here at 40-something AU. Neptune sits here at 30. And so these red objects, even though their orbits are slightly elliptical, never can approach Neptune. And so they are stable where they are for billions of years, in fact, for the age of the solar system. And so that's why they're there. They haven't been kicked out by Neptune. Neptune is the big guy that is responsible for the stability or instability of things in the outer regions of the solar system. The green objects are these bodies called the scattered Kuiper belt objects, which dip in near Neptune at perihelion. And at perihelion, Neptune gives them a kick, and then the kick causes their eccentricity to go up, and they basically get scattered along this arc that goes up towards infinity. When they go too far away, they get plucked off by passing stars, and they say goodbye to the solar system. And then the interesting ones right here are the blue guys. The blue guys are the resonant Kuiper belt objects, and these are 3 of the resonances marked right here. Jane gave you a diagram like this, but a very early version of this diagram with Pluto marked by an X. And so you all know which one is Pluto, right? No, not at all. So Pluto is there. And again, the deal is that we immediately knew Pluto is not special because on a diagram like this, it's just one of the dots. It's just another dot. So it was only special because it was discovered so early compared to the other objects. So let's talk a little bit about scientific consequences of the Kuiper belt. And let's talk about what I like to call, and some other people call, the inward armada. So the armada, remember, is this fleet of ships that Spanish people used to send to attack English people a long time ago. Yeah. So the Kuiper belt is like that. The Kuiper belt is like Spain. It's sending out things into the solar system. They drift inwards. They approach the planets. They get scattered by the planets. Some are ejected immediately into the interstellar medium. They're never seen again. Others are kicked into the next planet. or even into Jupiter and then into the inner solar system. So this is the inward armada, a set of bodies drifting inwards. Here's the same kind of diagrams, distance from the sun again, but now smaller. So here's the sun at 0, here's the Neptune at 30 AU. So this is interior to the region that we just focused on. And here again is the shape of the orbit. These dots here are called centaurs. And centaurs were discovered before we really knew what they were. They're distinguished by being orbiting in the vicinity of the planets. So Jupiter is here, Saturn is here, Uranus is here, and Neptune is here. These bodies cross the orbits of the giant planets. And that means that they're dynamically short-lived. When you encounter a giant planet, you cannot survive for long because it will throw you away. And so the question always was, where do these things come from? And we know the answer. They come from the Kuiper belt. So these are part of the armada of bodies drifting in. Kuiper belt is here. These bodies are diffusing in gravitationally. And when they come inside the orbit of Jupiter, the ice in the body gets so hot that it vaporizes and causes a transient atmosphere to appear. And then we say, aha, that's a comet. That's an active comet from the, now we say, from the Kuiper belt. So this is one of the great results of the Kuiper belt. We have this source population now. That's the source for the centaurs and source for the comets and a bunch of other things in the solar system. Previously, these things, believe it or not, were studied by different people. So certain scientists would study only these green dots. Certain scientists would study only these red dots. And there was no crosstalk between them, because why would you have crosstalk? Well, it turns out they're exactly the same animal, just in two different states of dynamical evolution, and they're even the same as the Kuiper belt objects from further out. So that's a great thing about Kuiper belt. It's a unifying influence on the solar system. Here, just for reference, is a picture of a comet nucleus. This is the only comet nucleus that's been visited twice by spacecraft. So here's a visit made in 2005, and here's a movie of a visit made in 2011. So you can see different sides of this thing. This is basically a small Kuiper belt object. But because it's been near the sun, it's been heated, it's lost a lot of mass, and the surface is evolved relative to the surface it would have in the Kuiper belt. So this is not the primordial surface. This has been affected a lot by the mass that's been lost by sublimation from this body. Still, it's pretty interesting. And compositionally, we can learn from the comets about the Kuiper belt and vice versa, because they're the same thing in different states of evolution again. And then another pretty picture. This is a comet from the Kuiper belt. This is a body that's only 5 kilometers across. It's very, very small. It's made of dirt and ice. It's been scattered in by Neptune. It's drifted inside the orbit of Jupiter. It's come close to the Earth. It's sublimating and releasing this material. It's very pretty. It's very spectacular. And now we know where it came from. And then just one more example. If you look at the sky before twilight in the morning or after twilight in the evening, you can see this structure called the zodiacal cloud. So it's a kind of a cone-shaped band of light that comes up from the horizon. And it turns out to be scattered by trillions of tiny dust particles. And there's been a discussion for a really long time. Where do those dust particles come from? Do they come from collisions between asteroids that smash and make dust? Or do they come from comets that are releasing dust into the inner solar system? Which one is the dominant source, or is there maybe another source? So now we know that actually this dust comes from comets, and that those comets come from the Kuiper belt out beyond Neptune. And so the irony is that the inner solar system, including the Earth, is bathed in dust that's ejected from vaporized Kuiper belt objects. We sit in this cloud of stuff, and the contribution to this cloud is about 50,000 kilograms per second, 50 tons of stuff per second coming from vaporized Kuiper belt objects. Now, let's just say a few words about migration, because that turns out to be really important. Migration occurs, is the change in the size of the orbit of a planet. The evidence for migration in the solar system is probably the biggest single most important scientific result following the realization that there is a Kuiper belt. So migration occurs because when a planet scatters a comet, imagine a planet orbiting the sun and it interacts gravitationally with a comet or a Kuiper belt object, the scattering event can cause the planet to transfer some energy and angular momentum to the smaller body. So gravitational interactions between Kuiper belt and Neptune, for example, result in a change in the size of the orbit of Neptune. So that's migration of the planet. Now, if you had a solar system with one planet and you scattered comets from that planet, the planet would have to move into the sun to provide the energy and angular momentum to eject bodies. But we have many planets in the solar system. So it turns out that in our solar system, the planets Saturn, Uranus, and Neptune have moved out, and only Jupiter has moved in. And Jupiter is this massive planet that's the source, the ultimate source of the energy and angular momentum needed to move everything out. So we have the evidence for migration from the Kuiper belt because the only model for explaining why those resonances are so populated is one based on the assumption that Neptune moved outwards. So Neptune is now at 30. We think that it started maybe at 20 or even 15 AUs from the sun, much closer to the sun, and has moved out into the Kuiper belt regions. It migrated out. And that is what has filled up those resonances. Like pushing a snowplow through the snow builds up a wall of snow on the front of the plow. Neptune pushing out into the disk builds up a pile of Kuiper belt objects trapped in the so-called mean motion resonances. So that's the idea. Now, I know that, here's a picture just to remind you of that. Those resonances are overpopulated because of migration. I know that people don't like resonances. So when I teach classes and I say the word resonance, people go, oh, I can just see. They don't like it. But resonance is a very easy thing to understand. It's just the language that people don't like. So you know that when you push somebody on a swing, if you push in phase with the natural period of the swing, you only need to give a little push when the swing is at the extreme position in its motion. And then the little push will just give a larger and larger amplitude if you keep on doing it at the right phase. You have to do it in phase with the natural period of the swing. And if you don't pay attention to the natural period of the swing, say you push here, that push is wasted. That's not going to increase the amplitude. So a small force applied at the natural frequency of a thing or system can lead to a big amplitude. Okay? So for a swing, we know what the period is. Just depends on how long is the swing. What about for a bridge? Well, these people were out walking, and they discovered natural period of the bridge is about a second, and they discovered that they can excite a big amplitude motion on this swing, on this bridge, excuse me, by jumping up and down in phase with the natural period of the bridge. So these people weigh a few hundred kilograms, and a bridge weighs many thousands of kilograms, but they're able to move it a lot by jumping up and down in phase with the natural period of the bridge. And you might ask, exactly why were they doing that? Sometimes it's better not to ask. And the gentleman at the back seems to be having altogether too much fun from doing this, so I'm highly suspicious. But anyway, so that's the idea of a resonance. What about for planets? Well, the natural period for a planet is the orbit period. That's the only period it has. So that's why we care about the orbit period of Neptune compared to the orbit period of a Kuiper belt object, and why we care about the ratios of the orbit periods, 3 to 2, 2 to 1, 1 to 1, whatever it is. So people have asked the following question, and these people were based in Nice. Here's Gomez, but there's a group of people based in Nice in France who've produced something called the Nice model, which is very interesting, and which might, in part, at least be correct. And so it's even more interesting. They asked the following question: what if the planets migrated so that two planets fell into a mean motion resonance? So the planets start with some position, and then they move radially relative to the sun. Their orbits expand or contract, as the case may be, in response to ejection of bodies from the solar system. What if that migration forces two planets that were not initially in a resonant configuration into a resonant configuration? Then you might think something serious would happen, because then you would have the circumstance where the geometry of the planets repeats, and so a small force, which is the gravitational force between planets, is then being applied periodically to the planetary system. So they made this model, and it shows 4 planets here. This is a disk of smaller particles, and you can see that the first thing is the outermost planet immediately throws up this arc, which looks like the arc of the scattered Kuiper belt objects. So it's very similar. These planets are jumpy because of recoil. So when a planet throws away a smaller body, it recoils in the opposite direction. So this is a jumpy motion. This is time in years. It's 400 million years elapsed since the beginning of this movie. I think it's 10 million years per second. And so it's settled in what looks like a steady state configuration. There's this arc. There's kind of a straight line there, which seems to bear some resemblance to a resonance location. And here's the classical Kuiper belt out there. Everything is looking good. But keep your eye on these two, which are Jupiter and Saturn, here's Uranus and Neptune. Jupiter and Saturn are getting close to a resonance. And when that happens, this diagram changes substantially. And it changes because the outer solar system basically explodes. And it explodes because this planet, which was over here, was thrown into the Kuiper belt. So the idea from this model is that the planets originally started, I'll just go back one step. The planets originally started in a compact configuration. Remember, Neptune is now at 30, Uranus is at 20, Saturn is at 10, Jupiter is at 5. This is a kind of a squished solar system. This is the Kuiper belt, but not today's Kuiper belt. This is a 300 times more massive Kuiper belt in order to get strong gravitational interactions between the belt and the planets. And so by letting this thing run, we can drive migration, and after about 800 million years, the system goes unstable, and this massive amount of material in the Kuiper belt is basically knocked out of the solar system and causes a shower of material to pass through the solar system because Jupiter and Saturn, those two, get into a resonance, and they basically shake the solar system to bits. And then, although it's not shown in this movie, the claim is made that miraculously the whole thing settles down and gives us the solar system we have today. So that's a very pretty model. I'll just let it run because it's kind of interesting to watch that. It's a very pretty model. It has issues, and the biggest one is that it doesn't make any testable predictions that an observer can act upon. So we find it hard to know if this is what really happened. It fits a lot of properties of the solar system, but we don't know if it actually represents what really happened. But it might. There you go. So that's one possible past for the solar system. So the thing to take away from that really is that the discovery of the Kuiper belt forces us to consider the possibility that models like this might be relevant. Whereas in the past, we just had a relatively static, not so interesting solar system in which the planets moved forever in perfect circles. And the solar system now looked the same as the solar system basically when it was born. This opens up the possibility that the solar system has changed a lot, and there might have been dramatic events responsible for the structure of the solar system that we see. So that's why, dynamically, the Kuiper belt has had a big impact on the way we think about the origin and evolution of the solar system. There are various things, various processes that could occur during resonance capture that cannot occur in the solar system today. So I mentioned that armada of bodies coming into the inner regions. There are other populations which are not now fed by the armada that might have been fed during this chaotic phase in the solar system. Basically, by throwing all these objects into the inner solar system, you can trap some fraction of them, a small fraction, into special locations. So we have things called irregular satellites, we have things called Trojans, and a bunch of other bodies that might have originated in the Kuiper belt. So it's kind of a unifying picture of the solar system. And then lastly, this thing with the debris disks. Debris disks basically are dusty rings around other stars in which the dust in the ring is younger than the age of the star. So that means that the dust was not there when the star formed. It must have been created since the star formed. And the question has been, how was it created? The model that people have produced is that the dust is created by collisions between larger bodies in an unseen ring around the distant star. So in other words, created by collisions between asteroids or Kuiper belt objects around other stars. So this is a picture of a bright star, a naked eye star. Now it's been blotted out by a black circle because it's so bright that it's frightening to point a telescope at it. But it has this dust ring around it. This is light scattered from dust towards us. This dust is probably produced by collisions between unseen parent bodies in the ring. Here's the same ring seen at a different wavelength. Here's the star, and here's the ring. Our solar system, we now know, would look like this from the outside, if we could see it. And our dust would also be produced by collisions between Kuiper belt objects out there. So this is a good thing because this means that people like me who are very interested in the solar system have something significant to talk about with people interested in stars, for instance. You know that science tends to be very compartmentalized and people become experts in some micro field. So it's always good when you find something that encourages people to talk sideways and broaden their outlooks a bit. And that's what we've done. So there's some significant dialogue and some significant modeling of debris disks and dust production in general. So there's that same summary that I gave you in the beginning. In case you were sleeping in the beginning, I'll show you this again at the end. Kuiper belt provides a very cold place, a deep freeze storage location for primitive material in the solar system. It provides all these different ways for subpopulations in the solar system, many of which were previously known but not really understood. It provides a kind of an umbrella for all those subpopulations to be connected and understood. It provides very interesting information about the evolution and formation of the solar system. For example, migration, is really a game changer in the solar system. It was something not considered. It just was not considered before the Kuiper belt showed that we need it to explain the resonant bodies. That's a really important thing that's led to a whole set of interesting dynamical models of the solar system and kind of a re-evaluation of what might have happened in the last 4.5 billion years. And then lastly, we have this connection to the debris disks around other main sequence stars. So I'll just end there. Thank you.
Thank you, Professor Jewitt. Could you please stay for the Q&A session? Would Professor Chu please accompany Professor Lu to go on stage and moderate this session?
Okay, now we're open for questions. Professor Yang.
Dr. Lu showed in her slide the discovery of 1992. Each of those little rectangles, how many such sized rectangles did you have to scan that night before you found this object?
Each of those images was just a small subset of the entire CCD image. We just cut out a little section to let it right.
Yes, but how do you know which direction to look?
The blinking process allows any moving object to jump to appear. It jumps out very clearly, as you saw. If I could show this, if I were able to show the slide again, you can see that during the blinking process, the galaxies stay the same, the stars stay the same, they stay fixed, but anything moving jumps out very, very
readily. You mean anything which moves?
Exactly.
Your system automatically will...
Exactly. That's what that movie was supposed to show.
Thank you.
So if you should look at the image, it's very, very clear. Any moving object would just jump out at you because everything else stayed fixed. Galaxies, stars, everything stayed fixed. Only moving objects jump out. So it was very easy to see.
Oh, I see. But if that is the case,
yeah.
Why was it not done earlier than you?
Because the detector was not big enough.
Because your CCD...
The new CCD was large enough.
Had more resolution.
More pixels. Cover a bigger area of the sky. It was a matter of technology catching up with the problem.
Okay, another question.
Okay.
It's 20 years since your discovery.
Yes.
Why does it's evidently a most important discovery. Why does it take 20 years for you to be recognized by 2 big prizes this year?
You have to ask the selection committee for that. We have no
for
idea.
example, is it because,
Oh.
say, during the year 2002, there were still people who say you did not make a correct discovery?
No. No, it's not. I don't know the answer.
So by 2002, it's already obvious that you had made
1992,
a
it was
great
first
discovery.
one. The first one, it was obvious. First one, people were, very, very excited.
Not everybody.
What?
Remember?
No, there were a few doubtful people, but all reasonable people were very, very
reasonable.
excited.
The reasonable people were, right.
And the connections, I tried to talk about some of the connections. The connections really expanded very fast. So people saw the implications for the structure of the solar system, for planetary migration, for understanding the origin of the eccentricities of the planets, for understanding the size distribution and the way in which bodies grow by collisional accretion of things. All those things started almost immediately, within a year of the discovery. So why we get 2 prizes at the same time, 20 years later, I have no idea. But it's nice, of course, it's very nice. It's good. Whatever the reason, it's good.
Professor Kwok.
Thank you very much. We used to think that comets and asteroids are different because comets have water. And now, as you show in the picture, when we take a close-up picture of a comet, the nucleus is just like a solid, looks like an asteroid. Now, what I understand from Dave's recent discovery is the main belt comets. And now they are so-called asteroids with water. Do you think these 2 things are one and the same thing? How do you think they are really separate classes of objects as we used to believe?
Right. So that's thank you very much. I'll be giving a talk about that tomorrow, actually, at another place. But it is true. We've found objects that seem to be hybrid objects. They're dynamically like asteroids, but physically like comets. And one explanation, the likely one for some of them, is that they contain ice. So we think there is ice in the main belt, asteroids, between Mars and Jupiter. And that's a place where previously people thought the temperatures were too high for ice to survive. But apparently it does. So the question is, where did that ice come from? And there are 2 trains of thought. One is that the ice was incorporated in the asteroid belt and preserved since the beginning of the solar system. So the ice formed in place beyond the snow line, which, as you know, is this critical distance in the protoplanetary disk beyond which ice accretes and instead of staying as a vapor, as a gas. That's one possibility. Another one is that the icy objects in the asteroid belt were brought in from a larger distance and captured somehow. So expert dynamicists have looked at that, and there is no way, for example, for Kuiper belt objects, which we know are icy, to be captured in the asteroid belt. It's just energetically not possible in the present solar system. But if you have a solar system in which the arrangement of the planets changes, as in the Nice model or some other model with expanding orbits, then there might have been a time when Kuiper belt objects could be trapped between Mars and Jupiter. So there are some people who suspect that a large part of the asteroid belt might have been captured from the Kuiper belt. And that's an interesting proposition. And that, in the future, might be testable, because if that's true, if we can go to the icy asteroids between Mars and Jupiter and measure their detailed chemical and isotopical compositions, then we should find that they're just the same as what we have in the comets and the Kuiper belt objects. Whereas if they're substantially different, that would suggest more that they formed in place. So we don't know the answer. This population was just discovered like 5 years ago, but it looks like it's pretty interesting.
There's a question in the back, in the middle. Yes.
The model animation you showed, it showed all the objects kind of getting flying away into the interstellar medium.
Yep.
Do some of them also fly off towards the sun and turn into comets?
Yeah. Yeah. So there's a huge, when this event happened, if this event happened at all, when it happened, there was a massive flux of material into the inner solar system. So the reason the modelers, in this particular case, delayed the resonance crossing for 800 million years was they wanted to match the distribution of crater ages on the moon. And the crater ages on the moon show a peak at 800 million years after formation. So these guys are trying to say that this cratering rate peak could be due to the clearing of the Kuiper belt from objects thrown inwards. Yeah. So objects are kicked in, they're kicked out. Of the ones that come in, some hit planets, some vaporize. They would be like short-lived comets. They'd all be gone by now. But the solar system back then would have been extremely spectacular. You would have wall-to-wall comets in the sky. It'd be very nice to see. And then a majority of these things hit the sun, because the sun is physically the biggest target in the solar system, and it's kind of going to mop them up. So yeah, a lot of stuff comes in, a lot of stuff goes out.
I'd like to ask a follow-up question on that. Has there been any estimate whether that could account for most of the water on Earth?
So again, that's my talk tomorrow. But I'll just tell you that perhaps, yeah, perhaps.
There's a question in the back.
So since the discovery of the Kuiper belt, you have opened up and solved some more questions concerning the dynamics of our solar system. So do you think now 20 years have passed, are there still important questions concerning the dynamics of our solar system that have not been solved? Because it seems most people really just focus on the chemical compositions of planets rather than the dynamics. And some people even turn the focus to exoplanets already. And even after your discovery of the Kuiper belt object, it seems the general impression is that things about our solar system are already done. So do you still think there are important questions to be answered?
No, the important questions of our solar system are not done at all. I think we thought they were done, but then we discovered the Kuiper belt, and that opened up a whole new slew of questions that are just beginning to be attacked. Right? We discovered this population, but we still don't. We find these different dynamical groups, and we don't really understand them very well. We have some ideas, but there are lots and lots of unquestioned questions that are not answered, details we don't know. So no, I don't think our solar system is done.
So here's the deal. So astronomers are very conservative people, and also they're very class-conscious people, and they've invented a class system in which the value of scientific research is related to the redshift, the distance to the object. So they have a class system in which the cosmologists are better than the extragalactic astronomers, who are better than the galactic astronomers, better than the stellar astronomers. And at the bottom of the pile are people like me and Jane. So that's what you get from astronomy departments around the world, actually. And there are various reasons why, why class systems evolve in societies, is to make people at the top feel good at the expense of people at the bottom. But you also know that people at the bottom are just as essential, or usually more essential, than people at the top. So think about that. Now, it's also true that if you go to the solar system, the planetary astronomer, the planetary scientists, those people have the opposite problem. So they're very interested in bodies in the solar system which are nearby, because their principal objective is to be able to send a spacecraft to those bodies. And so, what we did actually was find a crack between those people who apparently are interested in only the edges of the known universe and think everything else is known, which is patently absurd, and those people who really want to send a spacecraft to something nearby. Nobody was thinking about this region of the solar system as containing anything at all. So the true answer for why it was not discovered before is that nobody was looking. And the reason that nobody was looking was that nobody thought about it. And so in English, there's this statement, out of sight, out of mind. Right? So if you can't see it, you don't think about it. That's exactly the case. So in a way, it's good that the astronomers have been so biased towards high redshifts, because it left the door open for us to do something really cool. Yeah? And if people want to be that stupid, that's up to them. So it doesn't matter what other people think. If you find an interesting problem, just go for it.
Okay, that's a question.
Thank you. I'm still very interested in the way that you work, besides showing us what you did in the office. So my question is, what actually gives different orbits to the Kuiper belt objects, and how do you observe that? Is it just by looking at the images you took on the CCD, or? Okay, that's my question.
So we take pictures mainly. So these are faint. So pictures are the easiest thing to do. From a picture, you can measure brightness. So the brightness can tell us something about how big is the object, and maybe a little bit about what's it made of. But the other thing we can measure is the position. And then if we take a bunch of pictures at different times, we measure the position as a function of time. And then from those measurements of position and against time, we can fit orbits. So that's where the orbits come from careful measurements of the positions from pictures like the ones that we both just showed. The other part of the question was about why are there different kinds of Kuiper belt objects? Yeah, it's in some cases we don't know, but in part it's because there are different ways to survive the disturbing effects of Neptune. So the classical objects can survive because they have circular orbits. They never approach very closely to Neptune, and so they never get a big kick. So they're just there. They formed in this disk around the sun, and they never really had a strong encounter with Neptune, we think. The scattered objects did and do, and so they're being kicked up into that arc. So they have a different style of interaction. They go up there. The resonant objects are stabilized by being in the resonance because of this periodic force that happens to keep them in the resonance, and so on. So there are different explanations for each class. But they all tell us something about processes in the solar system that we didn't previously think about.
Thank you. It's very interesting to notice the busy work that you were doing in the movie, that you are moving around, eating and walking and so on. I'm just wondering whether the work can be done more automated. I mean, like in terms of the search that you are doing, can it be done by computers? I mean, like you just form a hypothesis and then try to ask the computers to do the search for you, rather than you sitting around and then looking for things in the sky through the CCD camera.
In theory, you could maybe write a computer program to do all of that, but you can't predict what each given night is going to give you. So you go up there, you can't predict the weather. You might have some idea. You can't predict what clouds are going to come across the telescope. You can't predict everything about the weather, and that affects what you do. You also can't predict what shape your instrument's going to be in, what shape the telescope is going to be in. Is a CCD going to work? Is it going to be focused? So all these things you're checking all the time. Is the computer working properly? Are the data being downloaded properly? Are there hiccups in the data readout? So all these things you can't predict. So you could write a program to do all the work that we do, and you know what you point the telescope and so on. But there are all these factors, the unpredictable factors that you have to take into account when you make the observations, and I don't see how you can program that in.
But people do. People try.
Right.
When we did the discovery measurements, that was not really an option. So another unspoken component of being successful was we had a computer that was powerful enough to read out the camera. So it turns out the camera was so big that computers at that time struggled to read out the camera in any reasonable time and then display it on a screen. And so I remember the computer literally was struggling to do that. And then to add another computational layer in which you would have to go through the images and search for every object would have been too much. So it would have been nice and clean and all the rest of it to do that, but we wouldn't have had any result because it never would have worked. So in fact, looking by eye was the most efficient way to do that. And the other thing is the eye, people denigrate the eye. Oh, the eye is no good, you've got to use a computer program. The eye is really good at detecting moving things for a very clear evolutionary reason. When you're out there in the jungle and something unexpected moves in the grass, that could be a lion that's going to come and bite your head off. And so we have all these circuits in our retinas and our brains for detecting small movements. And those are the ones that we employed to find the Kuiper belt objects. So we are the computers. We have excellent computers called brains and eyes, and they're really, really, really good. And there is no software that can beat them, actually.
Second question from upstairs.
Hi, my background isn't in astronomy or physics, so this might be quite a basic question. But I don't quite understand how, when the planets interact with the small Kuiper belt objects, why there would be some of them being ejected rather than captured by the larger planets. So perhaps it's sort of basic explanation of the gravitational forces would be really helpful. Thanks.
Could you wave your hand so I could see you?
She's up. She's up.
I'm upstairs.
Look up.
Oh, okay.
Here I am.
I'm sorry, could we explain?
Yeah, I just wanted to know how
Why they're not
the
captured?
interaction between the planets and the Kuiper belt objects, why these smaller objects would get ejected rather than absorbed by them. It's just, I don't quite understand the gravity sort of part of it.
Sure, so if they're on, and hello to everybody up there. So if they're on an intersecting path, of course they'll be absorbed. They'll hit the planet and they'll be absorbed. But in general, it's very hard to capture a body. So think about it in terms of the energy. If the third body is initially unbound, energetically not bound to the object, to the planet, to make it bound, you have to dissipate some energy. You have to lose some energy. You have to slow it down somehow. But the question then is, where do you get energy dissipation in space? Because the solar system is a nearly perfect vacuum, so there's no friction. And so to lose the initial energy of motion of the particle in its orbit around the sun and then make it captured and orbit around a planet is extremely difficult. And people have struggled for decades, really, to find ways to make that happen. Because there are some bodies that seem to have been captured in the solar system. They're not that common. But we don't really know how that could occur. We have conjectures, but we don't know what happened. So capture is actually a very, very difficult thing to do, is the answer, because the solar system has no friction.
So do the objects get ejected by sort of going around the planet and then sort of flying off?
It's a kind of a slingshot. Right. So maybe you've heard that to send a spacecraft to the outer solar system, the energetically most efficient way to do that is to send it by rocket to Jupiter, have it pass by Jupiter in the right direction with the right speed, and then it falls into the gravitational well of Jupiter and comes out the other side with a bit more energy than it had when it went in. And it picks that energy up from the orbital motion of the planet around the sun. So it's a slingshot interaction that causes the ejection.
So in the model that you showed us by Gomez, when the two planets, Jupiter and Saturn, got into resonance and then they kicked a whole bunch of Kuiper belt objects out. Yep. Is that a similar thing, or is that quite different?
Is that what?
Is that similar to what you're describing here, or is it actually a different process that caused the ejection?
It's the same process.
Yeah, it's the same thing.
Okay.
That process causes a massive ejection and injection of material inwards and outwards.
All right, thank you very much.
Sure.
Okay, because of the time limit, we can only take one more question.
Susu.
Susu.
Say it again.
Why are some people so narrow-minded?
Why are some people narrow-minded? Probably because it's easier to be like that. So the progress of science basically encourages people to be very narrow and very specialized, and discourages people from not being like that. So that's just the way it is. It's easier to be narrow-minded than to be broad-minded. But it's much better to be broad-minded than to be narrow-minded.
It's always the harder way.
Okay, so with that, let's thank both of our speakers again for such an exciting talk and a wonderful question and answer.
Thank you, professors. We shall now call upon Professor Benjamin Wah, active Vice Chancellor of the Chinese University of Hong Kong, to present the souvenirs to Professor Lu and Professor Jewitt. Professor Wah, please. Thank you, professors. Could you please stay for photo taking, and would Professor Chu please join us? And in this memorable moment, would the following VIPs please also go on stage and join our photo taking? Professor Yang Chen-ning, Professor Kenneth Yong, and Professor Andrew C.F. Chen. This is the end of the lecture. Thank you for joining us today, and we wish you a nice evening.